Hey, all right. I'm gonna go ahead and put up the warm up now. Actually, let's see. So, um, for the following sequences of functions, determine whether, or let's see, determine the pointwise, dang it, limit f, whether fn converges to f uniformly on 0, 1, and whether, oops, fn converges to f uniformly on 0, infinity. So just two sequences here. The first one is fn of x is x to the n over 1 plus x to the n. And then the second one is fn of x is x to the n over n plus x to the n. All right, so let's say we'll resume at 5:15. All right. So hey guys, let's go ahead and go over the warm up here. So I'm gonna just go to a new page. So for the first one, for fn of x is x to the n over 1 plus x to the n, right? Calculating the pointwise limit should be relatively straightforward. So let's see. How would you describe the pointwise limit f? And let's also, I mean, we're kind of only considering x in 0 infinity. So don't worry about negative values of x. Right, so the pointwise limit, right, remember, the way you get the pointwise limit is you imagine like picking a specific x value and then just taking the limit as n approaches infinity, right? So if we imagine like what happens to this, if we think of x as a constant and let n approach infinity, then the behavior is kind of dependent on what x value, like there are sort of like three things that can happen, right? If the x value we started with was small, then as n approaches infinity, these will, x to the n will approach 0, right? So fn will just approach 0. So for x, let's see, so it's going to be like a piecewise function, right? So we have 0 for x in 0, 1, open, right? When x is 1 precisely, right, then this is just 1/2 for all n. So this is 1/2 for x equals 1. And then when x is greater than 1, x to the n approaches infinity as n approaches infinity, right? So so this overall expression approaches 1, right? So this is 1 for x in 1 infinity, right? So like to graph it, you know, you'd get let's see. So if this is 1, then we would have this, you know, open point here, and then like, right, and then like that. That's the limiting function. And the idea is that you know, the way the fn's look, it's kind of like that. Oops. I think something like that. Okay. And this asymptotically approaches 1, of course. So the question is, does fn converge to f uniformly on 0, 1? There should be like a 1-sentence answer to this. Anyone? Yeah.
Is it the fact that it is asymptotically similar? Does that just mean that it's uniformly convergent?
So not quite, right? Because so when you say asymptotically, sorry, say that again.
Like, is it just because, like, looking at the graph, we can see that it stays between those asymptotic lines? Is that enough to tell us?
Oh, you might be thinking of uniform continuity. So like in this case, fn actually is uniformly continuous, and that is kind of like partly because it's bounded, I guess. Like that could be a way, you know, you could kind of that's part of the reason why it would be uniformly continuous, I guess. But we're asking whether it converges uniformly, right, on 0, 1. So for uniform convergence, remember the idea is like we have to be able to pick, like for any epsilon, if we were to draw kind of like a bubble around, or like a a band, around the graph of the pointwise limit, right? So the pointwise limit is this like horizontal piece plus this point, right? So something like, right? So then the idea is that the value of Fn eventually, like we have to be able to find an n big enough so that like the value of Fn, the graph of Fn stays completely inside of this band, right? That would be, at least that's one idea. Like that's sort of the definition of uniform convergence, right? There's actually an even faster way of, well, okay, so the answer here is no, okay? So no. Maybe now that I've said the answer, can anyone tell me why?
So there was a theorem in the book saying that the limiting function has to be continuous if
yes. Yeah. So f is not continuous on 0, 1. That's the problem. Okay. Or at least, yeah, that is part that, well, yeah, that's the main problem on the closed interval 0, 1. The limit f isn't even continuous. So since fn is continuous everywhere, right? So if it were to converge uniformly, the limit would have to be continuous, but it's not, right? So fn does not converge to f uniformly on 0, infinity for the same reason, right? What about does fn converge to f uniformly on the open interval 0, 1?
it should be still no.
Yeah.
Okay.
Yeah, very good. In fact, actually, a way of thinking about why that's true is like, even if it's hard to sort of like analyze the values of fn directly, the fact that we always know, so fn of 1 always equals 1/2, right? So the fact that fn of 1 is 1/2 and fn is continuous means that for any n, there exist values of x close to 1. Let's say, values of x somewhere in an interval like 1 minus delta 1 for some delta, such that fn of x is close to 1, or 1/2, sorry, right? So like if you pick a small epsilon and you imagine like this picture here, where here I have like epsilon, and I'm trying to say like, oh, well, we should be able to get fn to stay within this band. You should be able to say like, oh, that's actually impossible, because eventually the value, as you get towards 1, the value of fn of x has to increase to 1/2. So if epsilon is like anything smaller than 1/2, like if epsilon was a third or a quarter or something, right? Then eventually, no matter how big n was, there would be some values of x over here where fn of x would be bigger than that, right? So that would be bad. So even if you actually exclude the point x equals 1, it still doesn't converge uniformly. On the other hand, actually, I can just tell you, I won't go through carefully why, but it is true that fn does converge uniformly to f on anything of the form 0a for a less than 1. Okay. So the convergence is uniform if you actually cut off like a non-zero length piece of this interval that includes this point 1, because that's kind of the problem point. So once you cut that off, then like all of this stuff does converge to 0, and you can kind of bound the convergence. Like the worst behavior is always like right at the biggest value of x. So you can, since fn at that value of x approaches 0, you can kind of like bound the entire behavior of the function by that one point. And so you can show it converges uniformly that way. So anyway, so we kind of, you know, went through all of, you know, we kind of really dissected that one. So let's look at the second one. So fn of x is x to the n over n plus x to the n, right? Again, x is 0, infinity. So what is the pointwise limit? Let's see, pointwise limit. So what is the pointwise limit in this case? It's pretty similar, except for like one point. Right, so the same stuff happens. Okay, so when x is less than 1, right, these just approach 0, and obviously n increases, so that just makes it approach 0 even faster. So it's definitely still 0 for x in 0, 1, right? And then if x is 1, then you just get like 1 over n plus 1. So that approaches 0 as well. Oh, so actually, so this becomes like closed. Oops. Right. And then for the rest of them, it's 1, right? Because if x is bigger than 1, then these increase exponentially. So, I mean, I guess one way you could think about it is like for x bigger than 1, if you write it as like 1 over like n over x to the n plus 1, right? This clearly approaches 0 for x greater than 1, right? So, wait, hold on. Oh yeah, okay. Huh, weird. Yeah, so anyway, sorry. I was just like, never mind. But this is all right. So this is the pointwise limit, right? Any questions about that? Okay, so the question now is about the uniform convergence. So does Fn converge to F uniformly on 0, 1? What do you guys think?
I think it doesn't.
Okay, and why is that?
For like the same reason as for other example, like if you draw a graph, there's the point where it jumps up to...
Well, so the issue is that, okay, so let's draw a graph. So let's say this is 1. Okay, so at f of 1 is 1 over, let's see, fn of 1 is like 1 over n plus 1, right? So let's say this, here's 1 over n plus 1.
Oh, I guess the answer is actually it does.
Yeah, it actually does. Hold on, so...
Oh, it's like if you cut it off in the other example.
Yeah, basically, yeah. And then like, let's say this is 1. I think like, hold on. So when x is like, oh yeah. So yeah, it's a similar thing. It's just that this increase happens, you know, I don't know, after the point. Yeah, after x equals 1, you get this like kind of weird behavior. But yeah, so the fact that like even at x equals 1, this value is like approaching 0 means that you can, since actually you can just say like, well, I guess it's not trivial to show that f is actually fn is like an increasing function, but I think you can say that like we should be able to say, so for x less than or equal to 1, let's see, how would we do this? So I think you could say, so fn of x is, oh yeah, sorry, no, so this is easy. We can just say, so fn of x is like 1 over 1 plus n over x to the n, right? If this is like less than or equal to 1, then this overall thing is greater than or equal to n. So this overall expression is less than or equal to 1 over n plus 1, right? Sorry, x to the n is less than or equal to 1, right? Does that make sense? So if fn of x is less than or equal to 1 over n plus 1, so what I'm saying is like fn of x is less than or equal to 1 over n plus 1 for x in 0, 1. So like to demonstrate, like to sort of formally go through the motions of showing that it's like uniformly convergent, you can say like, okay, let epsilon be greater than 0, take n equals like 1 over epsilon, then for n greater than n, we have 1 over n is like less than 1 over epsilon. So fn of x is less than or equal to, well, okay. Right, because this is just 0, since x is in 0, 1, right? And then this is actually fn of x, since this is positive, right? And then this is less than or equal to 1 over n plus 1, which is less than 1 over n, which is less than 1 over, or sorry, this is epsilon. Right? So there you go. There's your proof that it converges uniformly. So yeah, it's like subtly different. So yes. So how about this one? This one is easy. It's like a 1 sentence. Right? So the answer is no, right? Because f is not continuous at x equals 1. Right? So the discontinuity, okay, the reason that we can't say this in the first case, right, is that when you chop off, when you just consider the closed interval 0, 1, like exactly, right, you're actually like chopping off the part of f that actually gives rise to the discontinuity here, right? Because you just end up with 0. Like f, the restriction, right? F restricted to 0, 1 is just 0. So it's continuous. Oops. This is like a great example of why it's good to be like familiar with sort of how restrictions work and how like continuity can change in passing from a function to its restriction. So it's continuous. Well, it's just continuous, right? But f is still not continuous at x equals 1. Even though x equals 1 is part of the domain of the restriction, the discontinuity goes away because you've eliminated all the values of f that are far away from 0. So yeah. So f is not continuous at x equals 1, so that automatically means this convergence can't be uniform. Okay? Any questions? So hopefully this is like just yet another thing where the goal here, I think, for you guys, I mean, for everyone, should be to get comfortable enough with the concepts of uniform convergence, like the concept of uniform convergence, to get comfortable enough with it to be able to tell just kind of from visualizing a sequence of functions whether or not you expect the convergence to be uniform, right? So again, this is like a situation where like I did not have this entire argument in my head when I said like I already knew, I just knew that the answer here was yes. Okay. I just knew this just from like sort of thinking about it a little bit and kind of thinking about what the graphs looked like in my head, right? I could tell that the answer was yes, even though I didn't even have this whole idea at all yet, right? So I just knew the answer was yes, and then once I tried to pursue the proof, like this stuff kind of made itself obvious. But having that instinct, like having the knowledge, being able to just see what the answer should be, like in a binary way, is like a really valuable skill. Because the thing is, like all of the like being able to sort of heuristically tell various things, like is something uniformly continuous? Is it continuous at all? Is a sequence uniformly convergent? Whatever. Like, is it convergent at all? What's the pointwise limit? Stuff like that. Being able to like do that stuff mentally quickly helps you in like piecing together larger arguments. Like if you're given some general statement, for example, like if you're, for example, if you're like trying to disprove a statement, then being able to like think quickly about this kind of stuff is like very helpful in constructing counterexamples, right? And especially if you just like sort of remember a bunch of like sort of examples of sequences that did converge uniformly and sequences that didn't converge uniformly in like different ways, right? Then it's like you build up this vocabulary of, you know, sequences of functions and stuff that you can kind of use as like building blocks for like constructing, you know, more complicated counterexamples to things or something like that, right? And whatever you end up constructing, like if you can tell quickly when a sequence is or isn't uniformly convergent, then like if you try to construct a complicated counterexample to something, you should be able to tell quickly whether or not it's actually going to do what you want it to do, because you've actually developed the skill of like sort of telling those things in an intuitive way, right? So anyway, yeah, I think it's definitely worthwhile to just kind of like meditate on these ideas and like what it looks like, and try to like really memorize, maybe even memorize the specific functions and what they look like and whether or not the convergence was uniform in various scenarios. But you know, anyway, if you the more you work with it, the more comfortable you'll get. Okay. All right, so that's enough about that. Let's look at another problem. Unless there are like general questions about, you know, any of the material. Okay. Here's another, wait, hold on. Yeah, let's try this one. So show if Fn is a sequence of uniformly continuous functions on AB, and Fn converges to F uniformly on AB, then F is also uniformly continuous on AB. So the book gives a hint. Try mimicking the epsilon over 3 argument in the proof that if Fn are continuous, then F is continuous, right? So that's theorem 24.3. Right. The thing about when uniform convergence happens, then the limit is continuous when the functions themselves are continuous. Right. So that's one approach. I will say there's a slightly different approach too, which I'm not 100% sure if it's easier or harder. They might actually be the same sort of amount of work involved, but they're slightly different approaches. So there are other approaches to this, I guess, is what I'll say. Okay, anyway, I think this is kind of a neat problem. So yeah, let's go ahead and make, so since there are only 4, I think I'll just make a single room for all of you guys. And yeah, let's come back at like 5:55, I guess. All right. So let's go through the sort of the suggested solution, and then I'll show you guys what I had in mind, which I think is actually easier. I was thinking about it a little bit. I think I might have a better solution to this, but anyway, yeah. So let's see. So what do we want to show, right? So we want to show that f is uniformly continuous. If we're just proceeding with the definition, right? So we would like let epsilon be greater than 0, and we want to pick a delta. Like our goal at the end, right, is like f of x minus f of y is less than epsilon, right? So we're going to bound f of x minus f of y by something. This is kind of where the epsilon over 3 argument comes in. So how would you guys phrase the critical sort of inequality here that we're going to exploit? What should I put on the right side here?
Probably same with the inequality before, but changing x naught into y.
Yeah, exactly. So there's going to be 3 terms, right? And we're basically going to be comparing, we're going to be using some like approximation, right? So we'll be comparing the values of f to the corresponding values of fn. And then we'll be looking at, we'll be controlling like how much fn is allowed to vary, basically, right? So we'll have fn of x minus fn of y. And then we would have fn of y minus f of x, or sorry, f of y, what am I talking about? Right. So we want to make each of these less than 3. So these 2, we can make less than or equal to, or like less than epsilon over 3 by the uniform convergence. And then this one make less than epsilon over 3 by the uniform continuity, right? So that's like, since we don't, again, like as with the original argument for theorem 24.3, we have to like do this. We have to do the outer 2 terms first. We have to like enforce that condition first, because that's what tells us which end to pick. And then we can't do this one, the middle one, until we know like what value of n we're interested in, right? So pick n such that you know, f of x minus fn of x is less than epsilon over 3 for all x in AB. This is possible, right, by the uniform convergence. And then pick delta such that for this value of n that we picked, right, has like fn of x minus fn of y less than epsilon over 3 for all x minus y less than delta in AB, right? And then for all x minus y less than delta in AB. This inequality here tells us absolute value of f of x minus f of y is less than epsilon, right? So I mean that's not actually too bad. It's like not hard. I mean, it's not so hard that it's like, you know, you dramatically like want to avoid doing this. I just want to show you my other approach. Did you guys have any other ideas for like how to approach this?
I think it's possible to modify the logic a bit, but it essentially comes to that the same inequality.
Okay, well, how would you modify the logic? I'm curious.
Maybe using proof by contradiction.
Oh, sure. Okay. Yeah. Yeah. You can do stuff like that. Here's my idea. So, right. If fn, this is just going to be another great little reminder of just how beautiful, how useful this can be sometimes, right? If fn is uniformly continuous on AB, what else can we do with fn? I'm trying to like really telegraph the idea here. What else do we know about uniformly continuous functions on open intervals?
They're bounded? Is that what you're
Yeah, true. But what more?
The Cauchy criteria.
Okay, yeah, they preserve Cauchy sequences. That's another thing. What's like, okay. You should get this like instinct as soon as possible. So whenever you see a uniformly continuous function on an open interval, remember that you can always extend it, right, to a uniformly continuous function on the closed interval, right? So there exists an extension okay. So then, so basically what you can do is like show that, so then show that f can be extended to AB continuously by showing that well, okay, actually, okay, maybe this is not as easy as I thought it was, but basically what you want to show is like, okay, fn, what would we want to show? That basically like the limit as x approaches a, for example, from above of f of x exists and equals, and, or that this exists and the limit as n approaches infinity of fn of a exist and are equal. And then I guess then it should be, then it's straightforward to show that fn uniform, that these extensions converge to the extension here uniformly. Okay. Actually, sorry. Okay, this ended up being more I kind of forgot that you have to like do all this stuff in the background first, which is kind of annoying. I was kind of only thinking about this part, which is like not that bad, but all right. Well, it's still a nice idea, I think. Okay. I think it's a nice idea. I think you should just always remember that, you know, you can do the extension thing. It's just good to remember that always. Even though in this case it didn't end up being as useful as I thought it would be. Yeah. There might be a more efficient way of doing all this stuff, because I think there's a lot of overlap between these different ideas. Basically, like showing this, I kind of feel like in some philosophical way, I feel like it automatically implies this somehow. But I don't, off the top of my, I would have to think a little bit harder about how that's true. Yeah. Anyway, but I think
wait. Oh, can I?
Sorry, go ahead. Yeah.
What's your idea that f can be extended continuously, that's only if f is uniformly continuous.
Yeah. If you
Okay,
can show
right.
that, yeah, if f itself can be continuously extended, that automatically means it's uniformly continuous, right? Because once you extend it, right, then you end up with a continuous function on the closed interval AB. But any continuous function on a closed interval is automatically uniformly continuous, right? So so once you restrict it back to the open interval, the restriction also has to be uniformly continuous, basically. I mean, that's just the logic. Like, there was a theorem that was like f is uniformly continuous on the open interval if and only if it can be extended continuously to the closed interval, right? What I just said before that was like exactly the logic of like the proof of that theorem going in the direction of like, if it can be extended, then it's uniformly continuous. I just kind of restated the proof of that. Yeah. All right. Anyway, yeah, I think I feel like there's like a way to like whittle this down and like refine this argument and make it a lot cleaner. But I don't know. Maybe it's worth just toying around with this idea a little bit on your own to see if you can like make this be a really like efficient, compact argument. But anyway, I think that's going to be it for today, unless there are any more questions. All right. Yeah. So I'll see you guys tomorrow then.
Thank you.
Yep.